We are on chapter 4. It's all about forces. So this is a slight deviation from the kinematics part of it. So we did kinematics, which is equations of motion in one dimension and then in two dimensions, and now we are slightly kind of going off to a slightly different area, which is also a very big part of mechanics, and that's about forces. So we'll learn in detail about forces and what forces can do and the consequences of forces. And of course, you'll use equations of motion when necessary. Okay? Whenever it's needed, you will end up using equations of motion. So equations of motion are, those are equations that will kind of help you solve certain problems or situations. So you have this, you have this, you have this velocity. All right, you need to know the acceleration in order to go forward with the forces. Then you will use equations of motion. Nobody has to let you know that you have to use equations of motion. So it's just part of it. Okay? So what's a force? What's a force? Just tell me in layman's language, what is a force? Just common meaning. What is it? I'm not asking for a definition. Yeah.
Something that acts on something else.
Something that acts on something else. Any other? What do you regard as a force? He's applying a force on this. Yeah.
Energy?
Yes, you need energy to apply forces. That's right. That will be our next topic. Okay. In order to apply force, we need energy. So that will be our next topic. Yeah.
A push.
A push or a pull. That's it. Force is a push or a pull of one object on another object. That's it. Force is a push or a pull of one object on another object. There's always like two objects, the presence of two objects. One object has to apply a force on the other. It can be in the form of pulling it or pushing it. Okay? So that is basically a kind of a meaning of what a force is. Now, what can forces do? What can forces do? So this is push or pull of one object on another object. What can forces do? Yeah, just let me know what it is. Doesn't matter if it's right or wrong. I'll make it right. Just go ahead. Forces can move an object. Yep. Stop an object when it is already moving. It can just come and stop the object. So if a running back is kind of running and somebody can tackle him and stop him, so apply a force, right? Yeah. So make an object move, stop an object. What else can forces do? What else can forces do? Think of applying a force on something and the consequences, what I'm asking. Yeah.
It can accelerate.
It can accelerate. It can accelerate an object. No, acceleration means it can be a positive acceleration, which is like picking up from zero, which is like making it move, and a negative acceleration, which is making it stop, right? Negative acceleration is from a positive velocity, it goes down to zero velocity. Yeah, so one word to describe all these things is accelerate. It can accelerate an object. What else in terms of, like these words, what else can a force do? You apply a force and the consequence is this. Change direction. Changing the direction of an object. Like a soccer ball is rolling that way and you just hit it or pat it, it just changes the direction, but it goes the same speed. So let's say it goes with the same speed. All you did was deflect it. right? So you're deflecting it, which means basically you're changing the direction. And how did that change of direction take place? A force. A force came in, and that's how it changed it. So change of direction. What else? What else can a force do? Say anything. Anything the forces can. Other than these things, other than move, stop, change directions, accelerate, other than that, is there anything else a force can do? If someone applies a force on your face, what can it do? Come on, yeah. Break an object. Yeah, it can actually deform an object. It can deform an object. Cause deformation. Like change the shape. Now the shape is different. I applied a force. We can deform an object. And sometimes the deformation is temporary, right? Or permanent. So you can have deformation which is like temporary or a permanent deformation. You can just damage it forever. Okay? Like a piece of rubber. If you are like pushing or stretching a rubber band, for example. Just take a rubber band and stretch it. Are you deforming it? Yes. And let go. It's back. So sometimes the deformation can be permanent. If you snap the rubber band, that's permanent. Now if you stretch it to an extent and then let go and it retains its original shape and size, then it is a temporary deformation. So you can have a temporary deformation, like your tires, they undergo temporary deformation because it's getting loaded from the top, so the tires are getting compressed, so you can see the change of shape. But once the compression is gone, it gets back to its original shape, right? So that is a temporary deformation. Whereas if you just put your brakes on all of a sudden and then like grind the tires on the road, then you're causing permanent deformation. It just scrapes off part of the tire. Okay? It can cause deformation. What else can a force do? What else?
Good morning, Trinity.
Well, I can add that also. I mean, to contain something in a certain place, you need a force. Yeah. Suppose I need to fix something with these screws. What is holding something very firmly is a nut and bolt, right? Yeah. Apply a force and hold something in place. So as long as that force is continuously there, it holds it there, right? What else? Good. Yeah, I never heard that from someone, but yeah, that applies. Answers can come from you. You just have to think. And then all of a sudden something will click, and sometimes that will be the first time someone mentions that, and that can be right. Okay? Yeah, go ahead. What else can a force do? Yes? Condense meaning?
Like coal that's condensed by gravity and like stuff being opposite.
Apply pressure?
Yeah.
Yeah, okay, apply pressure. Yes.
So you can change it the direction. Can it change the magnitude of something?
Well, magnitude is basically, you mean magnitude of the speed and all
Yeah.
that? Yeah, that is what basically comes in move and stop and accelerate. Yeah. What did I say? Yes, apply pressure. Yeah. So applying pressure requires force. Yep. What else? Yes.
It can heat something up.
It can cause heating effect. Yes. A force applied on something can really heat up things because the force is required for energy. That's what our next topic is. And then when you apply energy, then heat is a consequence. Okay? So force is needed in those energy transfers. In other words, energy transfers. A force is required for energy transfers. Yep. What else? I'm tired. Go ahead. Hurry up. Yes, you have an answer.
I was just staring at your ruler, and I've been wanting to say like rotate something.
To rotate something. I know that's the answer. Rotate something. Correct. Yeah, to spin it. I've been spinning this forever, so no one is noticing these clues. All right, here it is. To spin something, you need force. So it is not moving. I'm not moving it from its place, but I need a force to spin something, to open the door. You're not moving the door. The door is still in place, but you are rotating the door to cause rotation. Yeah. To cause rotation, yeah, you need forces. We'll be dealing with rotation also later on as we go on from chapter to chapter. We'll jump into rotation as well. So then you'll know why the forces are important. Okay, so forces can cause rotation. So a steering wheel, for example. Are you applying a force to turn the steering wheel?
Yes.
Are you moving the steering wheel out of its place? No. The steering wheel is still in the same place. The steering wheel is just made to spin. It is still there. Okay, so that is a different thing. Now, so those are things that forces can do, mainly. Now, what are the different kinds of forces? Yeah,
A push and a pull.
that's true. But now we are looking at the different kinds of forces. There are two kinds of forces. One is called a contact force. And the other one is a no contact force, which is also called field force. Okay. A contact force and a field force. Field force is a no contact. Those are two kinds, as we can generalize it. Now, what is a contact force? What do you mean by a contact force? Yeah.
Push or pull.
Yeah, requiring a
Contact.
a physical contact. So I push this book. So that's a contact. I make a contact with the book, and therefore the book is getting a force applied, right? I push the table, so there's a contact there. So contact forces are forces which comes as a result of a physical contact. Now, what are field forces? Field forces are forces which don't require a physical contact, and the forces will act. Now, what are the different kinds of field forces? What comes to your mind about field forces? Yeah.
Wind.
Hmm?
Wind.
Wind is a contact, actually. Wind is actually a contact. Wind is actually coming and hitting us. Again, when we deal with pressure chapters and all that, we will learn about it more. Yes, Andrew? Huh?
Gravity.
Gravitational force. Yeah, understand the word gravity is not a quantity. Gravity is just an entity, okay? It's like sound. Sound is an entity, light. But speed of sound becomes a quantity. Do you get it? The same way, gravitational force, gravitational acceleration, like they're different. So it's a very common mistake. Students kind of say gravity for everything. The word gravity is an entity and not a quantity. Do you get it? So you should be more specific about, I'm asking for what are the different kind of forces, then you say gravitational force. It's a very common thing, students jumping and saying gravity. But again, by gravity, the students mean gravitational force. Or sometimes, you're saying, all right, G stands for what? Gravity. No, it's not gravity. G stands for acceleration due to gravity. You get it? All right, so gravitational force. Any other?
Magnetic force.
Magnetic force. And then, any other? Yes?
Radioactive.
Radioactivity is a different thing altogether. It's not a force, but can be connected, yes.
Time.
Time,
Not like.
Yeah. Time doesn't come in at all. Any other type of forces where there's no contact required. At the same time,
Sound.
huh?
Sound.
Sound. Again, sound is not a force. What is that?
Static.
Yeah, you call it static, but look at that.
Electricity.
It's like a snake charming, right?
You did the splits.
Yeah. So what is that? Electrical force. Yeah. Electrical. Yeah. Electrical forces. Now you learn again about electricity towards the end of this year. Okay? The last part of this learning will be electricity, but a little bit. Actually, electricity is done in your senior year. We start off with electricity. We end up with electricity here. So give you some ideas about electricity. That's the last part of AP Physics 1. And then we take off with that same chapter and move on. Okay? Like, in the senior year right now, I just finished with electricity. Now I'm going to start with magnetism from tomorrow. So start off with magnetism, and then it goes electromagnetism. It goes like that. All right. So electrical force, what others? So you saw electrical force does not require a physical contact. As you see, it was like. Now combining these two, we sometimes call it electromagnetic force. We combine those two and we call it electromagnetic force. And then there is something called nuclear force. Well, the nuclear force might involve, maybe the nuclear forces are involved in radioactivity. Since you said radioactivity, I said there's a connection. So nuclear forces are involved in radioactivities. Now, which of this is the strongest force? Which of them is the strongest? Yeah.
Nuclear.
Nuclear is the strongest. That's the strongest. Now, what is a nuclear force? It's a force between protons and protons, neutrons and neutrons, and protons and neutrons. Between all the stuff inside the nucleus, there is a force. It's the strongest of all forces. Okay? Nuclear force is the strongest. Which is the weakest? Gravitational force. Gravitational force is the weakest. And now looking at which is a long range force, like acts at great distances even. Even at great distances it works. So which is the longest range force? Gravity. You see, from the sun to the earth, what is holding the earth in its orbit is the force from the sun. Look, what is the distance? So everything is, so this is the long range. Yeah, it is the weakest force, but it is long range. It can act long distances. And which is the shortest range?
Nuclear.
Nuclear, short range. Meaning, as long as they are inside the nucleus, they will produce this force. And once they are out of the nucleus, if the distances are a little too much, even atomic distances, then those forces are nothing. Even atomic distances, the force becomes nothing, right? So as long as they are so close inside the nucleus, then the nuclear forces act. So the moment they get separated by even a bit, the nuclear forces are down. And these are the average strength and average range. Average strength and average range are those forces in the middle. But let's come to, reality. In reality, there is no such thing as contact force. What is this contact force? Contact force is when you touch something, right? There is no such thing as touching. I'm not touching now. That's a reality. So what exactly is happening is when one object goes close to the other object, what is on the objects? Atoms. And what's outside the atoms? Electrons. So what happens is when one object gets close to the other object, the electrons are getting closer, and electron spinning creates magnetic fields. So basically it produces electromagnetic forces. So what we are kind of undergoing is, we are experiencing the electromagnetic force, which is actually a no contact force. But those things act only when you're pretty close. So the moment you get close to an object, those forces begin to act. Literally, you cannot touch one atom to another atom. There's always a gap. In fact, one atomic diameter is the minimum distance to which you can go. One atomic diameter distance is the minimum you can go to. You get stopped over there. So when I touch something, although we look at it and say, all right, I'm really in contact, but actually there's no contact. It's not a contact. You are too close to it, and the force that you're experiencing right now is an electromagnetic force. So everything is coming to this. All the contact forces are electromagnetic forces. All the friction, that's electromagnetic force. Now what is friction? Friction is a force between two surfaces, right? Friction is the force between two surfaces. See, when I move my hands like that, I experience friction. Or when I push this book on this table, there's friction, right? There is a friction. There is an opposition to my movement. What exactly is friction? It's force between these two surfaces, between the book and the table. Now, where is the force coming from? To understand that, magnify the table surface so many times, and magnify the book surface so many times. And then you will see the table is like this. That's the surface of the table, which you cannot see. It looks very smooth, right? It feels very smooth. But magnify it, it'll look like a grassland. Under a microscope, this table will be seen to have a lot of ridges. Now the book, magnify the surface of the book is also like that. So that's the surface of the book, and that's the surface of the table. Now when you put them together, what's going to happen? It's like clinging onto each other like that, right? It clings onto each other. So when you try to move, now what is clinging onto each other? Those are the grass of atoms. Atoms are not like flat. The endings of those atoms are kind of poking out, like that's why I kind of use the word grass. So it's like this. So when these atoms are sitting on the other atoms, there is a kind of clinging action. And when you try to drag one object with the other object, what are you trying to do? You're trying to kind of peel those atomic layers, right? See? Can you see that? I mean, you try to peel those atomic layers, these atoms are kind of trying to restore itself back to its original position. So it's kind of trying to come back. And you have to apply a force to beat it, right? You have to apply a force to beat it. So what happens? You can actually, if you are stronger, then you beat the frictional force. So you kind of start slipping over the atoms. So friction is because of that. So friction is an electromagnetic force. And we think that this book is actually touching the table? Not really. It's close. And because it's close, it is experiencing electromagnetic forces. And when you try to drag it, all those electromagnetic forces are trying to come in and prevent you from dragging it. And that is what is friction. You'll learn more about friction later on, but understand the idea of friction is it's an electromagnetic force. There's no contact force. In other words, there's nothing that is in contact. Am I standing on the floor?
No.
I'm not standing on the floor. I'm just levitating right now. And so you are also. We're just like close enough. And when you are close enough, that grip on the ground is holding us in place. And since we are close enough, there's an electromagnetic force, which is actually what we call as a contact force, coming in and stopping us. We can't go too close. We are atomic diameter distances already, and that's where we stop. We're kind of supported, cushioned. So we are stopped over there. So that's not a contact. Saying that everything is not a contact at all, don't go and touch a girl and say, all right, I didn't touch you, I just came close to you. It doesn't work. Because in the physical world, touching is when you actually like make a force appear on the other side, then automatically it is touching. So even if someone stabs somebody else, the knife is not touching the person. It's just getting too close. And when it's getting too close, the force it imparts on the other body becomes too strong that it can rip the skin, rip the flesh, and all that stuff. It is just that it is getting too close, that's all. Okay? And the force also can produce sounds. Now see, I didn't touch the table. I just went so close. When I went that close, the table experienced that force and started setting itself into vibrations. So when you hit a drum, you're not really hitting the drum, you're getting close to it. And the drum starts shaking because of that. Yeah, that is the reality, and that's how if you microscopically look into it, there's no such thing as contact force. But we can't be looking at everything microscopically. That's why contact force is when you make a physical contact. Let it stay like that right now. So when I'm standing, we call that as a contact force, right? Because we are literally touching it. And that force is coming in because you're too close. So that is a contact force. Gravitational forces, electrical magnetic forces, and nuclear force, those are considered field forces. Those are considered field forces. All right? Good. Now, forces. There are 3 laws relating to forces. And all those 3 laws are given out by Newton's. Yeah. Newton's laws. So there are 3 laws of Newton. We'll go through it one by one. First law, second law, and third law. So let's go to the first law. It's very important that you know the real understanding of the first law. So when you are, faced with a certain situation, you should say, all right, according to first law, that is supposed to happen. So you should be able to pinpoint or reflect back onto those laws and give that as a justification for your for your answers. So what is this first law? First law, you can write it down. Write down the first law. Every object will stay in the same state of motion. Every object will stay in the same state of motion. unless acted on by net or just say unless acted on by unbalanced external forces. Unless acted on by unbalanced external forces. That is Newton's first law. Every object will stay in the same state of motion unless acted on by unbalanced external forces. Now, every word has to be thought about. So let's start from the beginning. Every object will stay in the same state of motion. What do you mean by same state of motion? What's a state of motion? Yeah.
At rest.
Or
In motion.
in motion with constant velocity. Okay? You can write that also down. Same state of motion implies what? Implies at rest, that's one kind of state of motion, or moving with a constant velocity. That's the other state of motion. When you say same state of motion, it can be a motion with zero velocity, or it can be a motion with velocity. That's what you mean by same state. So every object will stay in the same state of motion unless acted on by unbalanced. What's the meaning of unbalanced?
Something greater than or less than the force that it already.
Okay, tell me what's balanced forces.
Same force.
Same forces. You balance something. That means you don't let it go one way or the other, right? That's balancing. Balancing means like you don't let it go one way or the other. So if you're balancing something, okay, when I'm standing like this, how many forces are acting on me? Tell me how many forces are acting on me right now when I'm standing like that? Two. Tell me the two.
Gravity and electric.
The gravitational force pulling me down, the earth is pulling me down, that's one of them. The other one is?
Electromagnetic, says you're touching the.
Yeah, let's not use the word electromagnetic, just use the word contact. So just say contact force from the ground. Okay? So let's not use sophisticated, the words electromagnetic and so on right now, although it is, but we'll still use the word contact force because that's what makes real direct sense. Okay, so when I'm standing like that, there are two forces acting on me. One is the gravity pulling me down, and the other is the contact force pushing me up, right? The ground is pushing me upward. Are those two balanced or unbalanced? What is the consequence right now? Am I moving down? Am I moving up? So which means it's balanced. You see? So what do you know about the gravitational force and the contact force right now? They are equal and opposite. So right now those two forces are balanced, which means the net force is 0. The net force is 0. That's why it is, I'm standing there. And this is what we call as balanced forces. So if something is balanced, then that object should stay in the same state of motion. The object should stay in the same state of motion. That's what it means. Like if I put this marker down here, how many forces are acting on the marker right now? Two forces. One is the weight of the marker down, the other one is the contact force from the table, right? Now, are those two balanced? Yes, because the net force is 0. So balanced means net force is 0. Unbalanced means net force is not 0, right? So right now, what is the net force acting on this marker? Nothing, and so it is staying at rest. Now watch the marker as I apply a third force. When I apply a third force from the side, is the net force going to be 0 again? No, now it's unbalanced. So when I apply a third force, so this is the marker sitting there, the two forces, and the other one is a contact force. Now remember, force is a vector quantity, and so we do express forces using arrows. We draw arrows to represent forces because they are vector quantities. So you should be able to process forces the same way as we processed vector quantities. And I'll be drawing arrows which are longer, shorter, and at a different angle. And all that should make sense to you because vector quantities can be bigger, smaller, having different directions. So right now I've drawn those two arrows literally equal. So what's the net force? 0. But if I push it from here, the net force can never be 0 because there are three forces. Yeah, these two are balanced, but the third one is not making it balanced anymore. So what happens now? This marker is acted on by unbalanced forces. So because it's acted on by unbalanced forces, it's going to start moving. It's going to accelerate. It's going to accelerate. So again, going back to the definition. Every object stays in the same state of motion unless acted on by unbalanced. What's the next word? External. External force. What do you mean by external? That means there's an internal force as well. It is the external force that really makes an impact on the object, not the internal forces. An internal force is not going to do anything to the object. Like for example, you sit inside your car. You're sitting inside your car and you're pushing the dashboard. Can you move the car with that force? You can? Can you move the car by pushing the dashboard from sitting inside? That becomes an internal force. So sitting inside, you're not going to push the car. That's an internal force. External force is you get outside the car and push from the back. Yes, that means now you're an outside person. The same way, if I want to move forward, I can't just push myself like that. You know. If I push myself, I'm not going to go anywhere because I'm an internal thing. But if somebody comes and pushes me from outside, then that becomes an external force. Make sense? So external forces and internal forces. So internal forces can do nothing to an object. As it is, there are a lot of internal forces. Isn't there a force between the cap and this marker right now? There's a force. That's an internal force. But that's not going to do anything to the marker state of motion. You get it? That's where the word external. So again, every object is supposed to stay in the same state of motion unless acted on by unbalanced external forces. And that is the first law of Newton. So if I ask you this question, when the net external forces acting on an object is 0, the object must be at rest. True or false? When the net external forces acting on an object is 0, the object must be at rest. False or true? Why is it false? Yeah.
If an object is in motion, the force on the object can be 0, but it's still in motion.
Yeah. As I said, what is a state of motion? State of motion is either it is at rest or moving with a, yeah, you can have a constant velocity motion. You can have a constant velocity motion. If something is moving at a constant velocity like that, that's a constant velocity. Net force is still 0. You get it? A raindrop falling. Is raindrop falling with an acceleration or constant velocity? A raindrop. Remember, the raindrop is formed where? Like miles above, right? So imagine something is falling. You did the free fall experiments and all that, right? And you're using acceleration to do gravity to kind of work with it. Now, if you're dropping something from a 5-mile height, what is going to happen? It's going to really speed up. You can calculate and find out how fast is something supposed to reach the ground if it fell from 5 miles. If you use the equations of motion, you find out, and like how fast it's supposed to be hitting, like from a mile height. So if you say Vf square is equal to Vi square plus 2Ax, so Vf square is equal to initial velocity, let's say 0, and then 2 times 9.8 times, you're talking about, let's say 5,000 meters. Can you tell me how much is Vf? How fast is something coming down and hitting us? Calculate. Everyone. How much? No, did you take the square root?
300.
How much?
313.04.
313
Yeah.
meters per second. That's much faster than bullets. So in other words, if a raindrop was actually coming down at that speed and hitting us, it can kill us. Yeah. So things that are falling from outside, they can literally kill us because they're coming at such high speed. So a raindrop can literally puncture us. But thankfully we have the atmosphere, the air. The atmosphere is that blanket of air around us is supposed to really help us. So what is the air doing? It is offering air resistance. Because as a drop starts picking up speed, it just cannot pick up speed too much, because as an object starts moving faster and faster, air resistance starts coming into play. The air resistance starts coming into play. You can't just keep on moving faster and faster. Like if you're a sprinter, there's a certain amount of force that you can put in, right? Can you go faster and faster and faster? No, there is a limit. Once you go to a certain speed, you reach that speed, and after that you can't go any faster than that because air resistance. Now you can try to minimize those air resistances and all that to a good extent, and then you can go a little faster than that. So when the raindrop is right on the top, just created, its acceleration is 9.8 because there's only one force acting on it, which is weight. Okay? The weight is acting on this. But after some time, what happens? The weight is still acting on it, but there's friction force building up. So now what is literally happening is the weight minus this is a net force. And so the acceleration with which it's going to move on is going to be reduced. What happens after some more time? The weight is still staying the same, but the frictional force builds up further. After some more distance, after some more speed, the weight is still the same, but the upward force is nearly equal to this, nearly, which means the acceleration could be just like 0.5 meters per second squared. But is it accelerating? Yes, it is still accelerating. There is still some room for increase in velocity. But after reaching a certain velocity, the weight and the frictional force will just equal out. And when they equal up, what's the net force? 0. That means what's the acceleration? 0. Which means what will happen to the raindrop? Will it stop? No. It will continue with the same velocity because there's nothing to change its velocity now. There's no acceleration. So since there is no acceleration, it will continue to stay in the same state of motion, which is the same velocity. And so those raindrops are not going to come at this speed. They come at much smaller speeds, probably like 5 meters per second. The smaller the raindrop, the slower the speed. In fact, the very tiny raindrops, you can actually literally see them come down. You can follow it. Snowflakes, you can follow it very easily because they are still slower, like 0.5 meters per second. It can't go faster because air resistance builds on it very quickly because of its fluffiness. Right? So So that's why I said when you're dropping an object, try to take an object which is heavy and small and not having too many rough edges. Because if it has rough edges, it will suffer air resistance. Because to increase the time, you're going higher. But at the same time, if air resistance is there, acceleration initially is 9.8, but by the time it reaches the bottom of the thing, it is going to fall off to somewhere near 8 or even 7. Depends on air resistance. Now, if you dropped a ping pong ball, that would have given you an answer of like acceleration, overall acceleration would have been like 1 or 2 meters per second square with the ping pong ball, because it will reach its so-called terminal velocity very, very soon. Okay? So if a raindrop had no air resistance at all, this is the speed with which it will come and hit us. So the heavier the drop, heavier the object, the faster it's going to come and land. Hail, a piece of ice, are they coming faster than normal raindrops? They are. That's why they can cause damages. Rain, any amount of rain coming and hitting your car, nothing is happening, but the hail, that can cause damage, right? That can cause damage because they're coming faster. They are still not accelerating. They are coming down at a constant velocity, but they are actually coming faster than, much faster. But if there was no air resistance, look at the speed with which they should be coming down with. That would be a tremendous amount of speed. Anyway, so air resistance is something that we'll be talking about. For most parts, we kind of ignore air resistance, but later on we will bring in air resistance as well. Okay. So what is the first law saying? Every object will stay in the same state of motion unless acted on by unbalanced external forces, not internal forces, external forces. That is the first law. And the first law is also related to another word called inertia. The first law is related to the word inertia. What is the word inertia? Inertia is a tendency of an object. Is a tendency of an object to stay in the same state of motion. Tendency of an object to stay in the same state of motion. That's called inertia. Tendency of an object to stay in the same state of motion. You understand the term inertia, right? Tendency of an object to stay in the same state of motion. Now, why is there a tendency? Because some objects will require a bigger force to move it out of its place or to stop it. Imagine you have a bowling ball here and a ping pong ball here, right? Imagine you have a bowling ball and a ping pong ball. Which one has a greater tendency to stay in the same state of motion? Which one has a greater tendency to stay there? The bowling ball. Why? Because if I just blow like that on both of them, the ping pong ball is gone. It requires only a tiny bit of force to keep it going, correct? And that is why we say the bowling ball has more inertia than a ping pong ball. Now think of the other way around. Think of the other way around. Imagine a bowling ball is flying at your face. So wake up. Imagine the bowling ball is flying at your face and a ping pong ball is coming. A bowling ball and ping pong ball, both are coming to you. Someone threw a bowling ball and a ping pong ball. Which one is easier to stop? The ping pong ball. Okay, the ping pong ball has a greater, or its tendency to move, its tendency to stay in the same state is less. And so the ping pong ball is easy to stop. But the bowling ball is difficult to stop because you need a huge force to bring it to a halt. You get it? Think of a truck and a car. Truck and a car. Which one is easier to get going? The car. Easier to get going. That's one of the advantages, right? You know, when you're at a stoplight, or if there's a truck and you want to get in front of the truck, it's much easier to do because as soon as the stoplight opens up, the truck, by the time he kind of picks up, you can just go inside. Right? We take advantage of his slowness. Why is he slow? Because he's got a lot of inertia. Inertia is actually related to mass. Inertia is related to mass. More mass, more inertia. More matter, more inertia. That's how it is connected. So, tendency of an object to stay in the same state of motion, that's called inertia. And why is there the tendency? Because first law says for every object will stay in the same state of motion unless acted on by external unbalanced forces, and that is the reason also. So in order to move the ping pong ball and the bowling ball, you need to apply force, but you need a much bigger force to get the bowling ball going and less force for the ping pong ball to go. And that's another reason why, again, which one has more inertia, a truck or a car? Imagine they're both moving. They're both moving at the same speed. Which one is easier to stop? The car. The truck is not easy to stop. So that's one thing that you'll be taught, like at driving schools. Like imagine there's a truck right behind you, and you see the stoplight is just turning, red. Not red, but maybe it's about to turn red. So just as you see that, you don't hit your brakes immediately. You don't hit your brakes immediately. First, you look in the mirror and find out what's coming behind you. Is it a regular car? In that case, that car should be able to stop with you. Is it a truck? Then don't stop. Keep going. Don't stop. Even if it means that it just turns red and you're skipping it, it's fine. Yeah, because the truck is behind you, it is perfectly okay because the truck probably won't be able to stop in that distance. So if you deliberately stop, the truck will come and slam on you. So if the cops will actually ask you about it, you can always say that there was a truck right behind me and I saw that and it was a dangerous thing, that's why I just kept going. Yes.
I got a ticket for that.
Was it totally red or was it about to turn red?
It was like yellow turning red when I was going, and then as I was under it turned red, and then the cop gave me a ticket anyways.
Yeah, but was there a truck
Yeah,
behind?
there's a truck behind me.
Why didn't you say that?
I did.
Then
And
what?
he was like, well, I mean, you should have stopped because it was red. And I was like, well, the truck's going to run into the back of me. And he's like, I find that hard to believe. And I said, okay. And he gave me the ticket. A little citation.
Okay. Yeah.
It's on YouTube and there's a
So, let's say, for example, in a classroom, there's a heavy person, like a sumo wrestler, and there's a skinny person. Okay, and I'm just telling everybody, all right, can you all just get up from your seats and go one seat to the right? The skinny person will just spring up and move. What will the heavy one say? Really? Should I do that? The tendency of an object to stay in the same state. The fat one doesn't want to move. He wants to stay where put. That is inertia. That's mass. Because he has mass. And if you don't have enough mass, you're easy to go. And of course, the opposite is also true. Imagine a sumo wrestler and a skinny guy. They're both running downhill. They're both running downhill, and accidentally they trip on something, and they both fall. What will happen to the skinny one? The skinny one can grab hold to some grass or something like that, and then he can stop. He just stretches his hands, he can almost stop there. But the heavy one will keep rolling all the way to the bottom, because there's no way to stop him. He has a tendency to stay in the same state of motion. He has got a velocity, he will keep going at that same velocity. That is inertia. You understand the concept of inertia altogether? And you can see that happen so many times, like, okay, in a bus. If you're standing in the bus and the bus driver starts the bus, what will happen to you? You fall backwards. Why? Because This is you, and that's a bus. Okay, so when the bus takes off, you fall backwards because you are trying to stay in the same state of motion. Because you have inertia. Because you have inertia, you stay in the same state of motion. But the bus is moving forward because there's a force applied on the bus, so the bus is setting off. So what is happening is the bus is setting off, but you are not applied by any other force, so you want to stay back. And the same is true when it applies brakes. So you are on the bus and you are actually moving with the bus, and the bus suddenly applies brakes, not like that. The bus all of a sudden comes to a halt, like that. Okay. So what happens then? Your inertia will take you forward. And that's one of the reasons why we have seat belts and all those different things. Because if you're driving at 70 miles per hour on a road, your car is moving at 70 miles per hour and you are also moving at 70 miles per hour as an object. If the car goes and hits somewhere, the car is brought to a rest because of an external force on the car, but there was no force on you yet to stop you. And therefore, you will fly out of the glass. Yes.
So, like, if the Earth stopped rotating, we all fly.
Yeah. Theoretically, yes. Because we are moving at such a high speed right now with the Earth. Suddenly, if the Earth stops, not we alone, buildings and everything will be like rolling. It'll be like going around, So now, why is the Earth not easy to stop like that? Because it has inertia. So it's not easy to stop. Now, football players, they're better off with inertia. That's why, when you go, some players actually, they go to colleges and then they are not really qualified to be there because they're not heavy enough. Because if you're not heavy enough, it's easy to stop you. So you may be running very fast, you may be quick, but you cannot just stop yourself. You cannot just keep going because you don't have much inertia. You're light. And so you can be tackled very easily. So if you have inertia and you're running with a ball, it's kind of tough to stop the person. You get it? So that is the concept of inertia, which is basically first law of Newton.